What I'd like to talk to you today about is really nothing short of a revolution in my mind, and that is a revolution to the past, a return to using an ancient practice of amending soils called biochar. And I've gotten so excited about this that I've started the U.S. Biochar Initiative, and that is a national network to connect people who are excited, interested, enthusiastic about producing and using biochar. And the piece that I want to add to that is ensuring the sustainable production and use of biochar. Okay, what is biochar? This is going to have a climate change focus because biochar has a very important role in climate change. We've got too much CO2, methane, nitrous oxide, temperature, and moisture, and concentrated dead biomass. Those are the problems. The carbon cycle, we're pulling things out of the lithosphere, throwing it into the atmosphere at a rate faster than nature can absorb, ameliorate, or neutralize. So, what are we looking at? What can we do with all that dead biomass, and how can we break that cycle in some way? Biochar is zero waste and carbon negative. Can it be done? Yep, you can. What is biochar? This is a very complex definition, and so I'm going to make it easy for you. It's simply charcoal made from plant material waste in high temperature ovens with limited oxygen. And when you put it in the soil, it sequesters carbon for thousands of years. It's carbon negative because it holds carbon that otherwise would be in the active cycle. We're putting carbon back in the lithosphere and holding it there. Therefore, it becomes carbon negative. And biochar also has a lot of other interesting features. Because of its porosity, which I'll show you a picture of soon, it attracts water and nutrients, holds them, making it more bioavailable to plants. It also creates great habitat for microbes, and that means that we'll be able to use less fossil fuels because we're giving a place for the nutrients to reside and feed back to the plants. Yeah, it's charcoal, but when you do a close-up, a square centimeter or a cubic centimeter of biochar can have thousands of square yards of surface area. Wonderful for microbial habitat. Biochar used to be made something like this, and in many places it still is being made like that. That's not a good way to go. Now these are pyrolysis ovens here, and that's actually in the upper corner is a microwave. And in New Zealand they're experimenting with microwaving entire bowls of trees. Interesting. Not sure I'm convinced that that's the best idea, but it's working. So what's pyrolysis? Thermal conversion of biomass in limited oxygen environment. What is really good about it is that you capture the gases that are coming off and feed it back into the system. It's not combustion. Combustion results in ash, and it's in open air, lots of oxygen environment. You can pull a lot of things out of a pyrolysis process. Syngas, which can be used as a substitute for propane, bio-oil, and biochar, that soil amendment with the carbon sequestration, also possible for carbon credits. And you can also be heating an area while you're converting this, and then take that heat and convert it to electricity. And there are very, very low emissions. This is looking at the amount of CO2 coming out of the biomass, go through pyrolysis, and you retain 50% of the carbon from the original material when you convert it through pyrolysis. Put that back into the soil as biochar, and then you also get some other energy products which contain the other 50% of carbon. Biomass now, instead of a waste product, is renewable energy. It's a soil amendment, and what's really interesting is that it reduces nitrous oxide off-gassing out of soils by 50 to 80%, and that's really important because we use fossil fuel-based fertilizers in most of the major agribusiness. So if we are throwing that nitrogen out in the soil, what's happening, nitrogen likes to move. So it's going to move off the soil in runoff, or move into the soil and then off gas as nitrous oxide. Nitrous oxide is a greenhouse gas, but it's 310 times more powerful than CO2, making it a real nasty greenhouse gas. Also, charcoal, we've been using that for filters for years. biomass or biochar acts like a filter because it'll grab that nitrogen and the phosphorus, which is a limited compound in the world anymore, and it will hold it. It also grabs heavy metals and it raises pH. So if you are in soils that need liming, you don't need to lime if you're using biochar in that. And you don't have to keep putting biochar in time after time after time. You just slowly build up the amount of biochar in the soil to an optimum level, and you're done. There are, oh, I'll get into the history here. Putting the bio in the char, our soils and plants here. Where'd it come from? Well, we're discovering it's not only Amazonian Indians 2,500 years ago, but people living in jungle areas in Africa were using, instead of a slash and burn, they were slashing, they were cooking the materials that they slashed, creating char and working that into the soil, most likely along with all kinds of organic waste as well. That's how they were able to support large cities and populations in jungles where notoriously poor soil. Well, you know, you can eat fruits maybe, but that's in a small clan kind of arrangement. You can't support a large city unless you are actively conducting agriculture. The terra preta soils, that's dark earth soils, are still fertile today in the jungles, in the Amazon. It's absolutely amazing. They produce 5 times more food and plant growth than straight jungle soils. That's a tremendous benefit for the farmers that are still living there today. Can you imagine giving a gift to future generations that lasts thousands of years by improving soils? Good picture of, this is a terra preta soil here, and these pits can be anywhere. The terra preta can be 6 feet deep. I mean, these people were working it. That's regular jungle soil. This is the terra preta. There's a profile there of different levels in the soil as you go down. We've already talked about most of this. It also improves soil texture. By making the nutrients more available, again, less fertilizer and greater plant growth. Here's a photograph of no biochar, 8 tons per hectare and 20 tons per hectare in Colombia. And you can see the difference in the plant growth here in a typical maize field. This is just talking about half-life of the carbon. The carbon sequestration values, if we ever had a carbon market or a price on carbon emissions again, you can see that it can really ramp up even at $30 a ton, where it was hanging about $30 to $35 a ton in Europe. And so you could get $100 a ton for your biochar in addition to the other benefits that you could get from it. Renewable energy, heat, power, syngas, bio-oil, substitute for fossil fuel, and it puts waste to use. If you want to, people have asked about, can you pyrolysize municipal waste and create biochar? That has too much crap in it. We don't know what that crap is, and we don't want to deal with it or put it back in the soils. So if we are going to use pyrolysis for municipal solid waste, you want to do it at a very high temperature, which will produce the least amount of char, and put it back in a contained landfill. It's a toxic substance. So you don't want to just put it out on the soil. But the interesting thing is it will reduce the waste by 90% in volume. So you're only putting 10% volume back in the landfill. And so that can save on landfill space and save the pain and disruption of developing new landfills. Just showing you a pyrolysis setup that's producing electricity. This is in Calgary, feeding back into the grid. Canada happens to have some very good net metering, and so you can actually get a decent return on your money. Not so in the United States. Bunker, that's a picture of bio-oil there. It's a thick substance. Further refining adds a lot more energy inputs, and you want to really watch your energy return on, or energy invested on, energy return on energy invested. And so we don't recommend refining bio-oil to a biodiesel, which can be done, but it's more energy inputs, and we don't like the carbon footprint on that. Just some comparisons of what it can be used for. have to watch with bio-oil. It is heavier than water, so if you had a spill, that could be an issue. You know, I may sound like a snake oil salesman here as I promote biochar, but we have a lot of caveats in the biochar community, and we are very concerned with emissions, with the quality of the material, with the characteristics of the biochar, with the sustainability of biochar, and the big question is the biomass. We love it, we need it, we want it, but it can be over-harvested and it can be used in some very poor ways. According to us humans, biomass, any carbon-based material which, when sufficiently dry, can be thermally converted to energy and other byproducts. Yeah, right. Well, according to nature, biomass, a complex structure, nutrients, moisture, temperature regulators, shelter, food, homes, carbon sequestration. It's really important in situ. But nature produces an excess of biomass, so how can we intelligently use the surplus? Permaculture principle. The functions of biomass, you're probably quite familiar with this, but it's good for the soil and the water. It's important in the carbon cycle. It's certainly important in erosion, in holding snow, in riparian cover that will moderate stream temperatures, which is going to be very important for our fish populations. And then plant health, the decaying matter is a source of nutrient, and it's also a source of propagation from live biomass, shelter for seedlings. And that can produce greater growth, which uptakes more carbon dioxide. All very important. Biomass critically important to animals. Also to the site ecology, moderates the wind effects, influences moisture patterns, retention and distribution, and also supports our lovely fungal world. So what should we use for biochar feedstocks? Well, pulpwood, which is insect-killed trees, again, not taking off more than is required by the scientific principles that dictate how much biomass tons per acre should be left on site to do all those important functions we just talked about. Wood waste from processing, that's a really good one because it truly is waste at this point. Forest slash and other thin materials. I have little stars by some of these things because we are concerned that these items be used sustainably. Now manure, if you don't need it, if it's excess to your needs in composting, it can certainly be pyrolyzed. Yard and urban forest trimmings is hugely important source because there's actually tons and tons that are produced and it's just taken to a landfill. Hopefully chipped and used for other purposes. Agricultural waste, bluegrass, spoiled hay or straw, bagasse, which is the residue from sugarcane production, or methane digester residue. This needs to have other dry materials mixed in it. You can also use algae residue from algae operations. Right now we've got a pilot program in Montana that is they've got greenhouses, they're using the algae for biofuels and then taking the residue, adding that with pulpwood, waste pulpwood, and creating biochar from that. The concerns. We don't want to use biomass indiscriminately for biochar. It should be the lowest use or the lowest on the spectrum, and anything that we can do with a higher and more beneficial use with biomass, we should be doing it. Certainly we shouldn't be using food or animal feed as feedstocks. We should not convert cropland to grow biomass or convert conservation reserve program lands. Industrial scale production and or collection of biomass is fraught with problems. Not impossible to do, but really something we need to be very careful of. Transportation carbon footprints and costs. We cannot work on the paradigm of centralized plants for biochar. We have to decentralize this because we have to consider the transportation costs for the biomass. And using an ecologically unsustainable amount of biomass from crops and forests. And very importantly, the effects on visual quality and wildlife habitat. I think I'll skip this section on the wildland-urban interface because it's more critical and germane to areas that live near very large forests, particularly on public lands. And the wildland-urban interface is where we all like to live because it's beautiful, but that's where the wildlife is and that's where fires are likely to start. And if you start messing in the wildland-urban interface, These are this is taken right from my home, so I know dead trees. Not the wildfire. Oh, it's really neat. There's an elk standing in the middle of the river there. They know how to get out of fires. I'm just, people are concerned, oh, you're using biomass. Well, the Forest Service literally cuts down and burns 1.5 gigatons per year just to get rid of the slash. So, that's what we're focusing on, stuff that's going to be open burned. And, basically what I come back to in addressing the sustainable use of biomass is we have to reconcile those two definitions, the human definition of biomass and and nature's definition of biomass. Okay, sustainability guidelines. This plays off the material I've just covered. The importance of balancing the physical, biological, and human dimension. They're all equally important. And we've developed a very rigorous set of sustainability guidelines. It's on our website at the USBI, which is biochar-us.org. And I've got little cards out there that are a reminder that you can go to that website and help us by giving us feedback on those sustainability standards. Okay, I have more pretty pictures of biochar in other presentations, but I can just shut this down and we can just talk about biochar.